Okay, so this is chapter 15. Start the timer there. This is chapter 15, and we're talking about probability rules, or rules of probability. It says nice, cute. Probability rules. Excuse the cough. All right, so in chapter 14, we talked about a trial, and we talked that a trial generates an outcome, and then we said the word is event. Could be any combination of things, but really what we've said is that event and trial are going to be really interchangeable for us. What we didn't talk about is sample space. And we didn't define sample space exclusively, but realistically when we talked about the Venn diagram, we had the universe, and which was all possible outcomes, and that's what the sample space is. When we think about the Venn diagram, we've got the box, and that's the universe. That's what the sample space is right there. Okay. So, this says right here a whole bunch of stuff, and it says when outcomes are equally likely, probabilities for events are easy to find just by counting. Now, what that means is that if you've got a whole bunch of events and the probability of them are all the same, then you can count how many there are. And then, this is lovely, when the k possible outcomes are equally likely, each has a probability of 1 over k. We'll talk about that in just a second. And for each event A that is made up of equally likely events or outcomes, probability of A is the count of outcomes in A divided by the count of all possible outcomes. So let's talk about that just for a second, because what we defined probability being is as success over opportunity, which means the number of successes over the total of all opportunities. So if I've got a die here, and we're talking about the probability of getting a 1, then we're talking about how many ones there are out of how many possible sides there are. That's fine. So success, there's one possible success out of all possible outcomes, which is 6. But what if this die had 3 2s and 3 4s? Then, if I said what's the probability of getting a 3, I would say, oh, well, there are 3 successes because there are 3 3s out of 6 possible opportunities. If we reduce that, however, because we have equally likely events, we have 3 3s, 3 4s on that special die that we have, then if I reduce that, then the probability of getting a 3 would be 1 over 2, which is what this statement right here is saying, is that if they're equally likely, because there are 2 possible outcomes, and the probability of getting a 3 would be 1 out of 2, which would be 1/2. But what we said that we're going to do is we're going to leave that fraction, instead of making it 1/2, we're going to make that fraction 3 over 6 and leave it as 3 over 6 because that gives us more information. Because it tells us how many possible outcomes there are exactly, and it tells us how many successes there are, that there are 3 possible successes out of 6 possible outcomes, and that is actually more information than 1 over 2 or 1/2. Okay, so the book says make a picture, make a picture, make a picture. And we talk about this all the time, we joke about it, blah, 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 blah. It's so funny, make a picture, it's so annoying. It happens every other chapter, it says it. It's going to be really helpful for us here, okay? And then we have the most common type of picture that we're going to make is the Venn diagram. And here is Mr. Venn right there, who looks like he really needs to trim that beard. And Mr. Venn's first name should be, if he's going to have a really cool name, should be Sven. And he should be Sven Venn. But I believe his first name is John. And this is the Venn diagram here. Now, thinking with the Venn diagram, if you were thinking that, you know what, I need to really get another tattoo, then the tattoo that you need to get would be this. And of course, we need the universe out here. And you would have I, heart, and then you have 2 hearts and they intersect because it's a Venn diagram, and you'd have something like this, I double heart Sven. So if you're thinking about a tattoo besides the formula for standard deviation, which would be the super coolest tattoo ever, okay, this is probably the next tattoo you should be thinking about. And if anybody from any other school is watching this, they're going to be like completely offended and whatever. Alright, so what we talked about before is the addition rule, which said the probability of A or B, and we said, okay, if I have disjoint events, meaning that, excuse me, that when we have the Venn diagram that the circles do not intersect, then the probability of A or B is equal to the probability of A plus the probability of B. So if I had something like I was rolling die and I said, okay, the probability of getting a 3 or a 4 unrolling that die would be the probability of getting a 3 plus the probability of getting a 4, which would be 1 over 6 plus 1 over 6, which would be 2, 6, and we would leave it as 2, 6. We wouldn't take it down to 1/3, we'd leave it as 2, 6, because it tells us that there's 2 successes out of 6 opportunities. But what happens if I have this statement instead? What if I say, what's the probability that from a deck of cards, I pull out a king, or I pull out a diamond? Okay, so if I pull out a king, or if I pull out a diamond, and check in the time, pull out a king or diamond, that means that we're talking about the probability of a king plus the probability of a diamond. Okay, I can do that. If I talk about the probability of a king, there are 4 kings out of 52 cards. And if I talk about the probability of a diamond, there are 13 diamonds out of 52 cards. And I add them together, and I get 17 out of 52. Okay, that seems like it makes sense. But let's look at it. Because if I've got kings, I've got the king of hearts, I've got the king of diamonds, I've got the king of spades, and I've got the king of clubs. And if I talk about the diamonds themselves, I've got the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So I add these and I add these. But the problem is once I take this king of diamond and I count it here, I no longer have this. So that means actually what I don't have is I don't have 17 out of 52. I have 16 out of 52. So how do I go from this and getting 17 out of 52 to getting the correct answer of 16 out of 52? And the answer is that what I've done is, if I think about this as the Venn diagram, here's the Venn diagram, this image is not drawn to scale, and here are the kings and here are the diamonds. These two groups intersect, and where they intersect right there, where's the king of diamonds. And what is that? That is the card that is both a king and a diamond with one event. So what I need to do is I need to subtract off that probability of getting a king and a diamond, which is 1. 1 out of 52. So I take this 4 out of 52 plus 13 out of 52, and we're going to break out the eraser here, and we're going to get rid of this section here because we know that this is wrong. And we're going to instead add in, subtract off that 1 out of 52, that intersection of those two groups, and I get 16 out of 52. So the general addition rule, and let's take that back up, the general addition rule for any situation is going to say this. For any two events A or B, or A and B, A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Meaning that any time that you see or, you're thinking, okay, I'm going to add the successes from this group, and I'm going to add the successes from that group, and then I need to ask myself every single time, is there an intersection of these groups? Are they disjoint? And the opposite of disjoint would be joint. Are they joint? And the answer is yes, they are. And if they are, I need to subtract off that intersection. If, however, they are disjoint, meaning they do not intersect, then what I'm actually doing is I'm subtracting off 0 because there is no intersection, because you would have two separate circles. So therefore you are technically doing this, but you're subtracting off 0. And you're going to get the correct answer. Okay, moving on over. Back in chapter 3, we looked at contingency tables and we talked about conditional distributions. When we talked about conditional distributions, we had the two-way table, and what we said back in the days of the Titanic, we would say something like, under the condition that you survive, how many people were from first class? And we'll take a look at that in a second because we're going to run out of time, and we'll be right back.